Hi, my name is Lily Whitesell, and this is the Black Hole Lab. The objective of this lab is to calculate the mass of a black hole. This black hole's gravitational force is acting on a star with a mass of 2 times 10 to the 30th power kilograms and is on a unique trajectory. To model this, we will use GlowScript code and a trajectory determined by an email address. The email address used in my code is lwhitesell3@gatech.edu. To find the mass of the black hole, we will need to find the net force of the black hole acting on the star at all points on its trajectory. This net force is due only to the black hole and the time between the data points. This time will be 1 day. 1 day is equal to 86,400 seconds. Some other information that is vital to this lab is that the change in velocity in this scenario is a non-zero number. The parallel component of the net force is simply dependent on if the system is speeding up or slowing down, and the perpendicular component describes the curving path or motion of the system. And the total net force is these two components added together. Some basic equations needed in this experiment are the following. Momentum is equal to the mass multiplied by the velocity, so thus the change in momentum will be the final momentum subtracted from the initial momentum. dp/dt is found by dividing the change in momentum by the change in time. This value is ultimately equal to the net force of the system. We will discuss more important equations later in this presentation. Now we start with our GlowScript code. The code has been adjusted to the star's given mass and proper email address and the proper change in time. Another addition to the code was a counter and a summation of all the masses of the black hole that will be found. This will become important later for finding the average mass of the black hole, which is our objective for this lab. Next, we move on to the breakdown of all the equations in the code used to find this mass, and the net force and the components on the star. To calculate the parallel component force, we will need p hat, which is simply the initial momentum over the magnitude of the initial momentum. Next, we will need to find the derivative of the magnitude with respect to time, or d magnitude p delta t. This can be found by subtracting the final magnitude of momentum minus the initial magnitude of momentum, then dividing by the change in time. Finally, the dp/dt parallel component can be found by multiplying d magnitude of p dt by the p hat value. This value is also equal to the parallel component of f net. Then to find the perpendicular component, we take the total net force and subtract the parallel component of the net force. Then we will use these values to find the average mass of the black hole. First, we will need to find the change in position, which will be the change in position of the black hole minus the position of the star, where the position of the black hole is the origin and the position of the star changes with its generated trajectory. Then to calculate the mass, we will use the equation, the magnitude of F net multiplied by the magnitude of the change in position squared, and finally this value will be divided by the gravitational force constant times the mass of the star. To find the average, we will use our sum and counter variables. The sum of all the masses of the black hole calculated divided by the total amount of masses found. This comes out to be about 2.01137 times 10 to the 34th power kilograms. When we look at the simulation, we see that the perpendicular component always faces the origin, and the parallel component is always tangent to the direction of motion. We see the parallel component, represented by the magenta arrow, grows as the star speeds up, and while it approaches the black hole, and slows down as it gets farther away. What does it mean? How the net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. The answer is that you can see the change in momentum, but not the change in the net force. Ultimately, in our experiment, the net force is equal to the change in momentum and magnitude. With a small delta t, the Fnet and dPdt values will equal each other as they were set to in the glow script code. What if? Imagine the black hole whose mass you found was removed, and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? We would not notice a difference because the position data would remain the same, and thus so would the net force. This was the Black Hole Lab. Thank you for listening.